Welcome to Sleep and Absorb. Find a comfortable position, close your eyes, and let yourself relax. Tonight, we explore dark matter.
Everything you have ever seen, everything you have ever touched, everything that has ever been detected by any instrument ever built, every star and planet and galaxy, every atom of gas and dust in the vastness of space, every form of matter and energy that physics has ever identified and studied and understood, accounts for approximately 5% of the universe. 5%. The other 95% is something else. Something that does not emit light, does not reflect light, does not absorb light, cannot be seen or touched or detected by any electromagnetic means. Something that is, in the most literal sense, invisible, and yet something that is there, all around us, threading through galaxies and galaxy clusters in quantities that dwarf everything we can see, shaping the structure of the universe through its gravity, while remaining entirely immune to our attempts to observe it directly. 27% of the universe, by current estimates, is dark matter. A further 68% is something even stranger called dark energy. What we can see and touch and measure, the ordinary matter that makes up stars and planets and people, is a thin, luminous foam on the surface of something vastly larger and more mysterious that we do not yet understand. Tonight we spend 20 minutes with dark matter. What we know about it, how we know it, what it might be, and what it means that most of the universe is invisible to us. Let your breathing slow, and let the darkness around you hold that thought gently. The existence of dark matter was not proposed as a theoretical speculation and later confirmed by observation. It was demanded by observation, repeatedly and from multiple independent directions, before anyone could explain it. The evidence came first, the mystery followed. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies about 320 million light-years from Earth. He measured the velocities of the galaxies within the cluster and applied a simple physical principle. The galaxies should be moving at speeds consistent with the total mass of the cluster as estimated from its luminosity. They were not. They were moving far too fast. So fast that the cluster should have flown apart long ago. The individual galaxies escaping each other's gravity and dispersing into the surrounding space. The fact that it had not, that it remained a coherent structure, meant that there was far more mass holding it together than the visible matter could account for. Zwicky called this missing mass dunkle Materie, dark matter. Decades later, the astronomer Vera Rubin, studying the rotation curves of individual galaxies, found the same problem at a different scale. In a galaxy rotating under the gravity of its visible matter, the stars in the outer regions should orbit more slowly than those near the center, just as the outer planets of our solar system orbit more slowly than the inner ones. They do not. The rotation curves of galaxies are flat. Stars at the outer edges orbit at almost the same speed as stars near the center, as if the galaxy is embedded in a vast sphere of invisible mass that extends far beyond its visible edge. Gravitational lensing provides a third independent line of evidence. Massive objects bend the path of light passing near them, as Einstein's general relativity predicts, by measuring how much the light from distant galaxies is bent and distorted by intervening galaxy clusters. Astronomers can calculate the total mass of the cluster from its gravitational effect on light. Consistently, the mass calculated this way is 5 to 10 times greater than the mass visible in stars and gas. Something massive is there that we cannot see. If dark matter is real, and the evidence that it is has reached a level of consistency and convergence that makes serious doubt difficult to sustain, then the question becomes, what is it? The honest answer is that we do not know. After decades of intensive theoretical work and experimental searching, dark matter remains unidentified, but the search has not been without structure. It has progressively narrowed the possibilities and ruled out a series of candidates that once seemed promising. The earliest and simplest hypothesis was that dark matter consisted of ordinary matter that simply was not luminous. Dim stars below the threshold of ignition, black holes, clouds of cold gas, large planets. These candidates are referred to collectively as machos, massive, astrophysical compact halo objects. Extensive searches for machos using gravitational microlensing have established that they cannot account for more than a small fraction of the observed dark matter. Ordinary non-luminous matter is not the answer. The leading theoretical candidate for most of the past 3 decades has been the WIMP, the weakly interacting massive particle, a hypothetical particle with mass in a range that would produce the right amount of dark matter through processes in the early universe, interacting with ordinary matter only through gravity and the weak nuclear force, which would explain why it is so difficult to detect. WIMPs emerge naturally from supersymmetry, an extension of the standard model of particle physics that was theoretically attractive for multiple reasons. Enormous underground detectors designed to catch the rare occasion when a WIMP bumped into an ordinary atomic nucleus were built and operated. None of them found anything. The Large Hadron Collider searched for supersymmetric particles directly. It did not find them. The most sensitive WIMP searches in history have returned null results. Other candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics that turn out to be viable dark matter candidates, sterile neutrinos, hypothetical cousins of the known neutrinos that interact even more weakly with ordinary matter, primordial black holes formed in the early universe before any stars existed, and more exotic proposals, including the possibility that dark matter is not a particle at all, but a modification of the laws of gravity that makes gravity behave differently at large scales. We simply do not know, and this is one of the deepest unknowns in all of science. The existence of dark matter, if it is confirmed to be a new kind of particle or field, rather than a modification of gravity, would represent the most significant discovery in fundamental physics since the development of quantum mechanics. It would mean that the standard model of particle physics, the most precisely tested theory in the history of science, is incomplete in a fundamental way, that there is an entire sector of reality composed of particles and possibly forces that interact with ordinary matter only through gravity, about which we currently know almost nothing. The universe is structured by dark matter in ways that determine the large-scale arrangement of everything we can see. The cosmic web, the vast network of filaments and sheets and voids that organizes matter on the largest scales, with galaxy clusters at the intersections and vast empty spaces between them, was shaped by dark matter fluctuations in the early universe. The galaxies we live in, including our own Milky Way, formed inside dark matter halos, drawn together by the gravity of the invisible scaffolding that was already in place before the first stars lit up. We live inside a structure we cannot see, that preceded us, that shaped the conditions for our existence, and that we have only recently begun to detect and map through its gravitational effects. Something is there. We cannot see it. We only know it exists because of the way it bends light and holds galaxies together and shaped the architecture of the cosmos. It is among the most extraordinary facts about the universe that most of it is made of something we have never directly detected. The darkness around you right now is not empty. It is threaded with dark matter, passing through the walls of your room, through the building, through the earth itself, in quantities that dwarf everything made of ordinary matter, moving at its own pace according to its own physics, entirely unaffected by, and almost entirely undetectable by anything made of the matter you and everything you have ever known is composed of. You are sitting inside an invisible structure that extends from here to the edges of the observable universe, a structure that held the galaxy you live in together for billions of years before the first human being looked up at the stars and wondered what they were. And that structure will be here, in one form or another, long after the last star burns out and the universe settles into its final, cold, dark equilibrium. We do not know what it is. That is the honest and complete answer. One of the most fundamental facts about the universe we live in is currently unknown to us, and there is something worth sitting with in that. Not with anxiety, but with genuine wonder at how much remains to be discovered, how young our understanding still is, how much of the universe is still waiting to be known. Let your breathing slow. You are safe. You are resting. And all around you, in the dark and the silence, something vast and invisible simply is. As it always has. Good night.